Welcome to Night Cosmos. Tonight, let's drift into the unknown. If you're new here, subscribe and join our cosmic journey into mysteries that stretch beyond the stars. Now close your eyes and breathe deeply. Imagine a particle that doesn't just defy the speed limit of light, it lives beyond it. This is the world of tachyons. They are theoretical, exotic, and possibly impossible. Yet, they've fascinated physicists and science fiction writers for decades. Could something travel faster than light? According to Einstein's special relativity, it shouldn't be possible. As you approach the speed of light, time slows and mass increases infinitely. But tachyons, if they exist, don't follow these rules. Instead, they would always move faster than light, slow them down, and paradoxically, they disappear. It's a puzzle of physics. A ghost in the math. So tonight, let's explore what tachyons are, where the idea came from, and why they challenge the very core of what we think is real. Relax, let the strange story unfold. The word tachyon comes from the Greek word tachys, meaning swift. It was first proposed in the 1960s by physicist Jarrell Feinberg, who explored the possibility of particles that could move faster than light. In theoretical physics, equations often have solutions that seem bizarre. Tachyons were one such result. They were not discovered in experiments, but appeared naturally in mathematics. Imagine a world where light is not the fastest thing. In such a universe, tachyons would be the rule breakers, existing in a different region of physics. They would have imaginary mass, not fictional, but a term from math involving the square root of -1. Strange as it sounds, these concepts are taken seriously by scientists when they arise from solid math. But what would a tachyon actually look like? Could it be detected? Could it interact with ordinary matter? These are the questions that kept physicists curious, and some still wonder today if they play a role in the deeper fabric of reality. Tachyons exist only in theory, but their presence in equations has sparked intense debate. In quantum field theory, the appearance of a tachyon often indicates instability, a system that wants to change. It doesn't necessarily mean a real faster-than-light particle exists, but it might suggest something deeper, that the current state of the system is temporary. Physicists call this tachyon condensation, a shift toward a more stable reality. It's a little like finding a ball balanced on a hilltop. It won't stay there long. The presence of tachyons hints that it will roll into a valley, a lower energy state. So in many ways, tachyons became less about speed and more about transition, change, and the hidden energy landscape of the universe. Yet popular imagination kept their faster-than-light nature alive. Could a tachyon carry information backward in time? Could it allow communication across vast cosmic distances instantly? These ideas remain speculative, but captivating. The line between science and imagination here is beautifully thin. Let's imagine how a tachyon would behave if it existed. Because it always travels faster than light, it could never slow down to our speed. To us, it might appear as if it arrived before it was sent. This leads to wild paradoxes, like receiving a message before someone writes it. In the framework of relativity, faster than light travel risks breaking causality, the idea that cause comes before effect. This is one reason many scientists are skeptical of tachyons existing in physical reality, but in some interpretations of quantum mechanics, time isn't a strict line from past to future. Some theories suggest that quantum particles can be influenced by future events. Could tachyons play a role in such strange effects? Possibly. No direct evidence exists, but the math leaves the door open. It's these thin cracks in certainty that allow ideas like tachyons to stay alive, not as proof, but as possibilities. The universe is under no obligation to make sense to us. Science fiction has long embraced tachyons as a plot device. In stories and shows like Star Trek, tachyons are often used to explain faster-than-light communication or time travel. It's poetic, really, how a theoretical particle can fuel the imagination of writers and filmmakers across decades. In these stories, tachyons bypass light-speed barriers, sending messages across space or even back through time. They are the ghostly messengers of the cosmos. While these portrayals are speculative, they're rooted in real scientific ideas. That's the beauty of science fiction. It stretches the limits of current knowledge while hinting at what might someday be understood. For many people, tachyons represent the ultimate what if. They occupy a space where curiosity thrives between known and unknown. So even if we never detect one, their legacy continues, inspiring both science and storytelling. In this quiet moment, consider how often discovery begins as a question, not an answer. Sometimes, wonder is the first step. Despite their exotic nature, tachyons have played serious roles in modern physics. In string theory, for example, the appearance of a tachyon indicates that a given string model is unstable. This doesn't mean tachyons are real, but it does mean the model needs to be refined. So, tachyons serve as signals, warning physicists that something in the framework must change. Some versions of string theory find ways to eliminate tachyons, stabilizing the theory. And in this way, they've helped guide the evolution of one of the most complex and promising theories in science. It's fascinating that a particle never observed can still influence the shape of physics. Think of tachyons like shadows. We may not see the object casting them, but their outline tells us something important exists, whether as instability in math or messengers in fiction. Tachyons continue to spark thought. They are not just about speed, they are about limits and what lies beyond them. One question remains: could we ever detect a tachyon? The challenge lies in their supposed nature. Traveling faster than light, they would defy traditional detectors, which rely on cause and effect. We need to rethink how measurement works. Some theories suggest that if tachyons interact with regular matter, they might leave behind faint traces, perhaps distortions in known particles or unexplained energy shifts. But so far, no experiment has revealed such signs. Physicists have searched in particle accelerators, cosmic ray data, and deep space observations. Still, tachyons remain elusive. This hasn't stopped the curiosity though. The search continues because even a hint of such a particle would revolutionize physics. It would challenge Einstein, reshape relativity, and perhaps unlock new paths through space and time. But until such evidence appears, tachyons remain in the realm of maybe. Like whispers at the edge of reality, they wait, imagined or real, calling scientists to keep asking questions. There's a paradox in tachyon theory that fascinates many. While we imagine them as fast, they actually become slower as they gain energy, opposite of normal particles. To approach light speed from above, a tachyon would need infinite energy to slow down. That means they can never reach or cross into sublight speeds. This forms a kind of mirror universe to our own. In this mirror, everything is reversed. What's slow to us is fast to them, and time might even flow in reverse. Some physicists use this framework to explore deep symmetries in nature. Could the universe have a hidden dual aspect, one where tachyons roam, unseen but influencing the whole? It's hard to say, but thinking this way helps researchers test the limits of physical law. The deeper we dive, the more we realize how much we still don't understand. That mystery is not frustrating, it's motivating. Science grows at the edge of the unknown, and tachyons live at that very edge. In some speculative models, tachyons are linked to dark energy, the mysterious force driving the accelerated expansion of the universe. While this connection remains unproven, it's an intriguing possibility. Both tachyons and dark energy operate in domains we don't fully understand. What if the vacuum of space isn't truly empty, but filled with strange fields? Fields that can host tachyon-like excitations. In this view, the universe may be influenced by particles we cannot see, moving in ways we cannot yet detect. It's a haunting thought, invisible motion shaping everything. Such ideas are speculative, but speculation has always driven science forward. Einstein once imagined riding alongside a beam of light, and that thought changed physics forever. Maybe by imagining what moves beyond light, we inch closer to another breakthrough. Even if tachyons remain in the realm of theory, they help frame questions we might not ask otherwise. In science, asking the right question is often more important than having the right answer. One of the most fascinating possibilities is that tachyons, if they exist, might allow communication across time. Imagine sending a signal into the past, not to change it, but to observe it. Could we one day build devices that use tachyon fields to peer into ancient cosmic history? Current physics doesn't allow such machines, but it also doesn't fully close the door. Some interpretations of quantum mechanics, like the transactional interpretation, allow particles to influence each other across time using advanced and retarded waves. One going forward, one going backward. If tachyons exist in this framework, they might be the messengers of time symmetry. They could whisper information not just across space, but across eras. While this remains firmly in the realm of imagination, it's not without structure. Real equations give rise to these ideas. So when you hear tachyon, don't think of fiction alone. Think of a concept born from mathematics, still waiting to find its place in nature. To appreciate the beauty of tachyons, we must revisit the speed of light. In Einstein's theory, nothing can accelerate to the speed of light because it would require infinite energy. This boundary defines the fabric of causality and time. But what if some entities were born on the other side of that boundary? Tachyons wouldn't break the rules, they'd simply play by different ones. Their existence wouldn't violate relativity, but redefine its domain. Some versions of the theory even treat tachyons as existing in a separate class of particles, never slowing down, never reaching light speed, always faster. Their realm is inaccessible to us and ours to them. We're like ships passing on opposite currents of time. This duality captures something poetic. Two worlds, separated not by distance, but by speed. The barrier of light is more than a speed limit, it's a wall between realities. And somewhere beyond that wall, in the math and mystery, tachyons might dwell. Throughout history, many scientific breakthroughs started as curiosities. Odd results in equations, misunderstood patterns, or ideas dismissed as impossible. Black holes were once considered pure fiction. Quantum mechanics was ridiculed for its strangeness. Perhaps tachyons are similar, a glimpse of something real that we don't yet understand. Or maybe they are simply a misstep, a ghost in the math, destined to fade. But even if they're never found, they serve a greater purpose. They remind us how little we know. They challenge our certainty and push us to test every assumption. In science, mystery isn't a weakness, it's fuel. The very act of pursuing questions like, do tachyons exist, leads to new insights, technologies, and even philosophies. In that sense, tachyons already have value. They spark wonder. They invite us to think bigger, reach farther, and imagine deeper. The universe is vast, and somewhere in its complexity, ideas like tachyons help light the path forward. Tachyons also raise deep philosophical questions. If faster-than-light particles exist, and if they can transmit information backwards in time, what does that mean for free will? Could the future influence the past? Would the universe become a predetermined system where every choice is already known, just not yet experienced? These are not questions with easy answers, but they reflect how physics and philosophy are intertwined. Science isn't just about numbers, it's about meaning. And ideas like tachyons force us to confront the nature of time itself. Is time a river flowing in one direction, or a landscape we move through? Tachyons, theoretical as they are, open doors to these discussions. And even if they're never observed, the act of imagining them helps us see our place in the cosmos differently. Maybe time isn't what we think. Maybe cause and effect are not absolute. In contemplating tachyons, we explore not just space, but ourselves and how we understand existence. There's a strange symmetry in the laws of physics. Many of them work just as well in reverse. If you film two particles colliding and play it backward, the math still makes sense. But in our daily lives, time clearly moves forward. Entropy increases, memories form, and events unfold. Tachyons challenge this perception. If something could travel backward through time, it would exist outside our arrow of time. Perhaps our experience of time's flow is local, a feature of our slow-moving, light-bound world. In a tachyonic realm, time might loop, reflect, or stretch. Some physicists think the universe may already contain regions where time behaves differently. If tachyons are real, maybe they come from such places. While these ideas are difficult to test, they're important to consider. They expand our vision. Science is not just a tool for solving problems, it's a way of asking better questions. and the best questions are often the ones that seem impossible. Tachyons may also tie into the future of space travel. Imagine if faster than light travel were one day possible, not by moving matter, but by manipulating fields inspired by tachyonic physics. Could we learn to surf on the edge of light? Some speculative drives, like the Alcubierre warp drive, rely on manipulating space-time itself, contracting it in front, expanding it behind. This doesn't violate relativity because the ship doesn't move through space faster than light. Space itself moves. Tachyons, while not directly involved, show us that physics isn't closed. It still has wild, untamed territories. Maybe by understanding these hypothetical particles, we'll unlock principles that make interstellar journeys real. Such ideas aren't fantasies, they're blueprints for dreams. Many technologies we now rely on began as impossible concepts. One day, the key to exploring distant stars may come from particles we once thought were pure fiction. For now, we watch, we wonder, and we prepare for what science may reveal. The story of tachyons is also a story of human curiosity. It shows how we grapple with the unknown, not with fear, but with fascination. To consider particles faster than light is to confront the limits of knowledge, and yet we push forward. Whether through equations or telescopes, our species is always reaching beyond. Tachyons are part of that reach. They may never be found, but they remind us that science is a living, breathing journey. Theories evolve, ideas collide, and sometimes impossible things become real. Just as once we thought Earth was the center of the universe, or that atoms were indivisible, perhaps our assumptions about speed and time will also shift. Tachyons are more than a particle, they are a metaphor for potential. They represent the spaces in our understanding yet to be filled. And in this quiet moment beneath the stars, we embrace the mystery. The universe still has secrets, and we're listening. Among those who study high-energy physics, tachyons remain a topic of debate. Some models predict them under specific conditions, especially in quantum field theory. In certain string theory frameworks, tachyons are seen not as physical particles, but as indicators of instability, signals that a system needs to evolve into a more stable configuration. In this sense, tachyons can be understood like tremors before a landslide, not the event itself, but a sign of deeper change. These tachyonic instabilities suggest that even abstract particles can influence how the universe reshapes itself. So while we may never trap a tachyon in a detector, we might feel its effects indirectly. A theoretical particle that doesn't exist in the traditional sense might still have consequences. That's the beauty of physics. It's not limited to what we can touch. Sometimes, unseen entities push the story forward. Tachyons, real or not, help shape the landscape of modern theory in subtle and unexpected ways. In the world of particle physics, discovery often comes not from seeing something directly, but from noticing something missing. Gaps in expected data, anomalies that don't align. If tachyons exist, they may leave such fingerprints, disturbances in the fabric of known processes. Physicists have designed experiments to test for faster-than-light influences, but results so far remain inconclusive. Still, the search continues. Instruments like particle accelerators probe the tiniest scales, hoping for clues. One day, a deviation in behavior, something subtle but undeniable, might point to tachyonic influence. Science is patient. We wait, refine, test again. Even if the trail runs cold, we gain knowledge. And if it heats up, then we stand at the edge of a revolution. Tachyons, long theoretical phantoms, could become part of our vocabulary, not as science fiction relics, but as pieces of reality. Until then, their absence keeps us honest. It challenges our tools, our models, and our imagination. Let's pause and consider why the idea of tachyons captures so much attention. Beyond physics, they symbolize something deep in the human psyche, a yearning to surpass boundaries. The speed of light is more than a number. It's a cosmic wall that defines our existence. To imagine something beyond it is to dream of escape. From time, from limits, from the known. In that sense, tachyons are more than particles. They are hope. A hope that the universe holds more surprises. That reality isn't finished revealing itself. Great science always begins this way, not with certainty, but with a whisper of the possible. Tachyons whisper loudly. Their story, whether proven or not, invites us to think beyond equations, to stretch the mind, to dream scientifically. That is their true gift. In a universe so vast, even a rumor of faster-than-light motion reminds us discovery is not over. Wonder still lives in the gaps of what we don't yet know. As we look to the stars, tachyons offer a new kind of navigation, not through space, but through thought. They show how strange and flexible reality might be. What if our assumptions about causality, speed, and existence are shaped more by perception than truth? What if light isn't the ceiling, but just one level in a vast structure of motion? In physics, paradigm shifts happen when we stop asking how things are and start asking what else could be. Tachyons live in that question, and though we haven't caught them, they lead us somewhere important, toward humility. The universe doesn't owe us clarity. It unfolds on its own terms. Our task is not to tame it, but to listen. And through that listening, perhaps one day, we will understand things that now feel impossible. Faster than light particles, time beyond sequence, realms we haven't even imagined. Tachyons may or may not be real, but the future they suggest just might be. Throughout this journey into the idea of tachyons, we've danced along the edge of known science and daring imagination. From theoretical equations to whispers of time travel, these elusive particles challenge everything we think we understand. They blur the line between what is and what might be, and yet they do so with elegance. That's what makes them fascinating. They're not wild fantasies. They are disciplined questions. Their existence might never be confirmed, but their impact is undeniable. They've inspired physicists to look deeper, question harder, and stretch the boundaries of what's measurable. In doing so, tachyons have earned their place not as facts, but as forces of curiosity. And maybe that's the real goal of science. Not to prove everything, but to keep asking, to keep wondering, to stay awake under the stars and say, what if? In that spirit, tachyons are already real. Not in labs, but in minds, willing to explore the impossible. Thank you for joining us tonight in this journey beyond the light. If you enjoyed this voyage through theory, time, and imagination, consider subscribing to Night Cosmos. Each episode brings you closer to the edge of what we know and what we dare to believe. Tachyons, though hypothetical, have guided us through some of the universe's deepest questions. What is speed? What is time? Can there be more than one reality layered within our own? These are not easy questions, but in asking them, we grow. We push our understanding of space, energy, and ourselves. And as we drift now towards sleep, let these thoughts settle softly. Let the unknown comfort you. The universe is vast, and your mind is part of it, capable of wonder, of learning, of dreaming. So rest well, traveler of stars. Tomorrow holds more mysteries, and we'll be here to explore them together. Sleep well, and good night from Night Cosmos.